קודם כל להציג את עצמי, אני ירון חביב, פאונדר ו-CTO של חברה בשם איגווזיו, עד... מה ניהלתי את תחום של...
אפשר באנגלית?
Until recently I was managing the data center activities in Mellanox and also was in charge of OpenStack development as part of that.
Sir, this better?
Okay, do you hear me okay now? One, two. Okay, take two.
Yeah.
So I'm Yaron. I'm founder and CTO of Iguazio, and until not too long ago, I was also managing data center activities in Mellanox, and OpenStack as part of it. What I'm going to talk today about is how to deploy big data on top of clouds and OpenStack specifically. I'm going to divide my presentations to two halves, roughly. One will talk about the challenges in big data, the common architecture of big data, how people do cloud and big data other places. Second half will be more focused on using OpenStack and the different tools within OpenStack to build an OpenStack big data cloud. Everyone asked me, how do you pronounce the name of the company? So it's Iguazio, and it's basically based on the Iguazu Falls, which are a very good analogy for volume, velocity, and variety. Those are in Brazil. A few words on big data. So big data is evolving rapidly, and we'll talk about the transition. And what we see in big data are three different needs. One is the need for high volume, meaning people starting to store petabytes, tens of petabytes, and even more data. People want more and more interactive response time, real-time behaviors to be able to extract value out of their analytics as soon as they can. And you have more and more variety. We started with log files, and what we could see today, video analytics, face recognitions, we could see clicks, we could see streams, Internet of Things sensors. So you have a lot of complexity when you try to address all those three challenges at once. If you just want to have volume, then you have a lot of solutions to deal with high volume at low cost. When we say volume, it's typically also scalable and low cost. When you want to do velocity, you have in-memory databases, key value store, all sorts of other solutions that only focus on performance, but they cannot deal with the emerging amount of volume. And what's really needed is a solution that comprises of all those three. One of the things that have dramatically changed in the last 10 years is the use cases in big data. When we started big data, which was Google inventing a new way of doing page ranking in the internet, and then sort of was taken to Yahoo and to others that started the Hadoop project, it was all about batch processing. So you upload all the data into a machine, very large log files, and then you have what's called a full scan. You read all the files, you analyze them, and you generate the results. And you work on batch processing. So that has totally different characteristics. It could run on physical machines. It needs local disks with sequential I/O. There's no importance to the data because it's just a staging environment. And as we see the new requirements in big data, they've changed dramatically. So we see that data is now being ingested in real time. People are talking about Internet of Things with millions or billions of sensors pushing data all at once, where video streams, etc. People want interactive response time. They want to run a query and be able to get the response now and not within a few minutes or few days. So all those things will impact the technology and the way big data is being re-architected. So one of the typical deployments of big data is this new architecture called the Lambda Architecture, which comprises of different elements to be able to address all those three V's of volume, velocity, and variety. The traditional first stage is the data ingestion or data sources. This is where you take the video streams or the log files or the streams from the internet or doing ETL jobs, basically extracting data from other data systems into this system. typically using sort of message queuing to ingest the data to deal with the high velocity, which is typically much higher than the ability of those Hadoop or other clusters to manage them. Once you've inserted the data into this sort of data lake, then you have different processing tiers. You have in-memory processing, which is dealing with sort of incremental data, small data sets, and basically analyzing and generating a subset of the data. We also have batch processing, which is more like the traditional approach, running over the entire data, extracting some meaningful insights, and then doing that in an iterative fashion. And in many cases, we combine the two. We will use in-memory where it makes sense because it's very expensive. It uses a lot of DRAM. And we'll use batch processing where it does make sense. It takes a lot of time, so we don't want it to deal with interactive analytics. At the end, we have other tools that will be able to visualize the data and do some more meaningful things with the data. What you would see, that there are many different requirements, especially for the storage piece within this data lake. What we end up having today when we deal with this architecture is many different tools or patches, and part of them are in order to deal with the specific limitations of the current architecture. So for example, we have caching layers like Tachyon on top of Hadoop file system because it's too slow. We have tools like Flume, which are log aggregators because we cannot update files in real time because it's not a real file system, okay? Each one of those tools, and we use Cassandra or Aerospike because on small objects it's not really working well. So we need something that's more optimized for small IOs and more random access. And each one of those tools typically is at least 3 copies, 3 nodes that need to run. Each one of them has consensus and all those things that are pretty complex to manage. And every guy that builds a big data infrastructure have to master all those tools, and they keep on changing. Every few months you'll hear about a new tool that was invented. The same tools have, same functions, have many different vendors. If you go to Cloudera or MapR or Hortonworks, you'll find different SQL tools for analytics. You have Impala, you have Hawk, you have all those things. So it's very complicated to build and manage. So companies that this is what they do for a living, SaaS providers will take a few months or years and they'll build this infrastructure. Guys that are in the enterprise have bigger challenges. Now when you go to an organization, you'll see that they have multiple applications. So you go to a bank and they have risk analysis, fraud detection, securities, etc. Each one of them is a separate big data cluster. And each one of those big data clusters are different tiers that if each tier have totally different hardware requirements, okay? So if you use Spark, you need lots of memory. And if you use batch processing, you need lots of capacity drives. If you use MongoDB, you want to use SSDs. So this is one of the challenges that each application it needs to be designed separately. And there's also no data sharing. Try taking data from one Hadoop cluster to the other, or from Cassandra to Hadoop, etc. And this is another challenge. So what would be the evident solution would be to use virtualization. Why won't we just use virtualization? We'll create those Docker templates or VM templates, each one with its own application, and we launch a bunch of them. So it doesn't really work because one of the biggest challenge in this environment is that Cassandra, Hadoop, Mongo, all those solutions, that basically they manage the disk. And if you introduce another layer of hypervisor that manages the disk, the performance will not be that great. All those things relates to high availability. Hadoop doing 3 replicas or the other solutions, they don't know how the hypervisor is organizing the data. So when they do 3 replicas, they don't really know where it lands, and you end up with no availability. And if you don't believe me that it's an issue, here are some results from the Vancouver event with OpenStack and Hadoop running in different scenarios. You could see that the bare metal Hadoop implementation would perform a certain degree, and then when you use the same configuration with this example is with the RAID 5 configuration, it's about 2 times slower, between 1.3 to 2 times, depending if it's read or write intensive. And you're supposed to get some aggregation through having more disks. This example is with what is called ephemeral storage. Basically, the applications owns the disk, but still goes through a hypervisor layer. running a traditional sorting benchmark, you see that, again, it's about 2.2 times slower than just running over bare metal. When we introduce Dockers, it's actually much better. It's only 1.5x slower. So we do need to deal with this problem of how to share data with big data applications. Another interesting point to look at is what is the growth of the data. You know, people are saying that in 2020, the amount of data generated per year will be 43 times more data per year than what it is today. So the growth is exponential. And if you take the aggregation of the data, is actually, you know, exponential squared. So we cannot just put disks in the machine like we used to do in EMC and have an exponential growth of the data. We have to be able to decouple the data from the computation. So what is the right solution? If we look at what basically Amazon would recommend, they'll say, you know what, build your, we have S3. It's infinitely scalable. It's very cheap, only 3 cents per gigabyte. Let's use that as sort of a consolidation layer. Let's throw all the data that we need to analyze into this sort of shared pool. Let's have all those applications run on top of this shared pool. And then eventually we'll generate results and we'll visualize them through other tools running on the same repository. Okay, now this architecture, which is used quite a bit by many Amazon users, is challenging. It's missing a few things. So the first thing is performance. When you upload things through REST, it's no problem. But when I want to run my Hadoop cluster on top of a RESTful API, that's probably going to be pretty slow. And one of the key challenges in all those Java applications is they're very synchronous. I don't know why. Java guys don't know how to write asynchronous code. But it basically impacts the dependency on latency. If I'm writing something that waits for the disk to return, then it means that if my latency to the I/O will be better, that means I do more transactions per second. So we have to lower the latency. We have to increase the performance when we access the data, especially from those applications, not necessarily from the clients or the consumers. The second thing is consistency. Most of the object storage in the world is eventually consistent. That means like Dropbox, you write something into it. When you read, you don't necessarily read the same thing you wrote. It may take some time, and then it gets updated. Now, if I have a big data application, one tier writes the data, and then another application picks up the data and needs to continue with computation, that's probably not a good idea to have eventually consistent. Another challenge that we hear a lot from customers is around applications in big data, not necessarily a right fit for the traditional S3 model. I'll give a simplest example that I hear quite a bit. If I need to do log aggregation, and that's a very common use case, what I need to do is basically add more log entries. Object storages or HDFS are immutable. That means I can only create a new file. I cannot add something to a file. So what do people do? They do log aggregation. They write another application, resides in a different VM, gets all the data, builds the files, and then generates a new file with a new name. Okay? Now, what happens if that virtual machine fails? That's a problem. So I'll replicate the same data in 3 virtual machines. So there I'm starting to gather a lot of complexity. If those solutions basically had the ability to add data in an incremental fashion, we didn't have to go through all that mess. And the last thing, because this is all shared storage, we have to focus on a lot more security. One better example is was just recently launched. That's something called Asier Data Lake. It's not even GA. It's going to be available only next month. And this is a sort of a better approach of a data lake. You see that they improve the performance quite a bit. They focus on latency for the right reasons that we mentioned. They allow ingestion and incremental updates and full file system access into it, as well as analytics on the same thing. So that's probably the right approach to build big data clouds, have something which is extremely elastic, allows you to grow the data exponentially, be able to expose these APIs both for the ingestion and the processing aspects. Okay, so with this sort of prefix, and now you know how it's big data and how it needs to be designed, this is the way to build it on top of OpenStack, okay? So what we need is a few things. First thing is sort of the virtual machines. And the virtual machines, we could use Nova with KVM or Dockers. We see more and more people working with Dockers. They're actually Two companies I know of that build this kind of a solution in an integrated fashion. There's a company called BigData and Altiscale, and they basically integrate that, and they all work with Dockers internally. So we need Nova. We also need network virtualization, all the things that were just talked about, because we want to have different applications running on different segments, and in some cases maybe higher level network services like firewalls and routing and load balancing. Okay, so we need the Neutron for the SDN piece. We need good shared storage. In those environments, Cinder is less relevant. Cinder is block storage. It's for virtual disks. If you're using Dockers, you don't need virtual disks. You need mount points on a file system. What you do need is a good object API and file API. And in OpenStack, you have Swift and Manila. The current implementation of Swift is quite slow, but you have those APIs. Many people, because they come from sort of an Amazon legacy, they also want S3. So although S3 is not an OpenStack API, it is required in many of those scenarios. And at the end, you do want something to orchestrate the operation, more platform as a service for big data. So OpenStack includes the Sahara project, and we'll get into Sahara and how it works. Okay, so this would be sort of an ideal configuration where I have this sort of shared storage or shared data lake. We have the ingestion from external users or consumption by external users of the data directly in or from the data lake. And we have the applications that access through sort of multi-tenant network into this infrastructure, and Sahara is sort of an orchestrator on top. Okay, so the first thing that not a lot of people know, that within OpenStack you have a project called Manila, which is like Cinder for block storage. You have basically a shared file system access. This is still relatively new project, but it allows you to basically have a shared file system mount that could be shared across many different virtual machines and maybe even external users. So this way, you can have a Hadoop cluster or another cluster that basically mounts the same shared file system and work on top of the data. And it's much faster than having object storage, and also allows modifying files, unlike object storage. Okay, so this is one tool that will need to be used. It's still not fully integrated with Sahara, but I believe that's going to be part of the next version. Another service in OpenStack is something called Sahara, which is the equivalent of Amazon Elastic MapReduce project. It's basically a full automation of the deployment of things like Hadoop and Spark, and it's extensible, so you could use other frameworks as well. So basically, you have a dashboard, and I'll show examples of the snapshots and how you configure and run your sort of Hadoop or MapReduce or Spark jobs. This is how it looks when you look at the screen. You could see it's called the data processing, and you could have different plugins for different Hadoop distributions or other applications. So what is the Sahara workflow? Basically, what we need to do is we need to create some images. That's sort of a one-time operation. Then we create definitions of clusters, of basically Hadoop clusters. And the Hadoop cluster is basically comprised of multiple subclusters. So you have this, and you create the cluster, and you launch it. Now you have a bunch of clusters. You want to run jobs on those clusters. It's another process where you define the job templates, and then you can run the jobs. So the idea is I have clusters, which are those virtualized clusters that can run Hadoop jobs, and then I have job items that run on top of this infrastructure. So how does it work? I basically can go and define, sorry, I don't see all the screen, but you can go and define the Hadoop clusters with all the capabilities, with which VM images to launch. And this cluster is actually multiple tiers, so I can define the cluster template, which defines which subclusters or which tiers I have within this cluster. Once I define it, I could just go and click launch, and basically launches a full-blown Hadoop cluster on my infrastructure. So I don't need to deal with all the issues related to installation and deployment of Hadoop. The other nice thing about Sahara is the ability to integrate the incoming, outgoing, or intermediate storage as a service. basically you have an API where you could define which mount points are part of this job, where you want to load data from, where you want to store data into, and you don't have to rely on the internal disks of the system. And the last item, when you define those, you basically define jobs. And you could actually define a job by just having a script, a pig script, or any one of those Hadoop scripts, and just launch it. Or you could have binaries that you upload to the system and then launch those binaries. And you could actually choose which cluster you want to run this job on. So again, very simplified. Assuming it all works, it's still, in OpenStack, not everything is still fully robust. But assuming this gets more and more robust, you'll have the ability to just go and launch jobs very easily on the cluster. Okay, so to summarize the session, then what we see is that big data have changed quite dramatically from batch-oriented jobs with fixed infrastructure to things that have to deal with high performance, elasticity of the data. It has to be pretty resilient. People now store in those things their crown jewels. It's no longer a staging environment where you upload data, you process, and then you throw the data. So you have to deal with all those issues. And those are the ideas that we talked about. And if we look at the cloud environment, big data is one of the key applications for cloud. If you look at how much energy now Google and Amazon and Microsoft putting into the big data services within their cloud, this is most of their focus. Okay, one of the key challenges of doing stuff in Amazon, you can upload the data, you cannot take it down. Okay, the cost is so high when you download data back, so it's good for basically storing data that you don't really need to use later. Okay, so this is the summary from my side, and by the way, we're hiring, and thanks.